I'm gonna let's. This is the recorded version. So now we're recording. Math 0310. We just finished exam one, and so I've got a couple of announcements that I want to make sure everybody is aware of. A couple people have already emailed me about this. I will post the grades on your WebAssign gradebook hopefully by Monday. That's my goal, at least, is to have them graded by the 19th of February and have them posted on WebAssign. If you don't know how to get to your WebAssign gradebook, when I do post them, I'll kind of send you some quick instructions on how to get there. It's actually easy to do. And so I'll put those grades on your WebAssign gradebook hopefully by Monday. When I do that, I will send an email, or I'm sorry, a remind message that I have posted them so that you know to go look for them. If you want your graded exam sent back to you, I will do that. But what you need to do is you need to formally request it, and so you actually just send me an email, and I will respond to that email with an attachment that's the graded exam. Do not send me a remind message about that. I do want it as an email. Same thing, by the way. I gave people extra points if they emailed me after the exam. There were some instructions on the front of the test. I don't want remind messages about that. It's hard for me to keep track of who has sent that stuff to me and who hasn't. It's much easier for me to keep track of it if it's an email. So please send emails for that. A day-to-day correspondence with me, remind is the way I want you to go. Or WebAssign. A lot of you are sending me stuff through WebAssign. But for that kind of stuff, go ahead and shoot me an email when you do that. I do want to point out, and I think I mentioned this somewhere to you guys by email or remind, but I have postponed by a few days the next WebAssign homework. The next WebAssign homework was due on the 18th, I believe, and I've postponed that through the 20th. So that will still give you next Tuesday's lecture to ask me any last-minute questions also about WebAssign stuff if you want to ask. And so that'll give you an extra couple days to look at that homework. So take advantage of that and try to get that homework done. I've got 2 assignments that are due on the 20th. So please get started on that. See if you can get that finished up. And yeah, so try to keep up with that. Remember, I do drop 4 WebAssign grades at the end of the semester. So if you do miss a grade here or there, that is generally not going to be a big deal. As long as I drop 4. So if you had 4 or fewer zeros, then it's not going to affect your grade at all. Even if you went over 4, let's say you had 5 or 6, there's a lot of WebAssign grades. So even if you missed a few that ended up counting, it really isn't going to affect your WebAssign average at the end of the semester by very much at all. And remember, that's 20% of your grade at the end of the semester. So, that's something that you can, as long as you generally do most of your WebAssign homework during the semester, you're going to be okay with that grade. One other thing, let's see, I didn't mention was that the final exam, and this isn't in your syllabus, but my final exam does replace the lowest exam grade. So if exam 1, for example, was not as good as you wanted it to be, right? If you didn't do as well on exam 1 as you wanted to do, it does not have to show up on your final average at the end of the semester. So because the final exam will replace that grade. And every semester, every class I teach, I have numerous students in the class who do replace a grade with their final exam grade. So in other words, their final exam is higher than one of their exams during the semester. And so it helps out their average a little bit. So don't think that that's a rare occurrence, okay? Let's say you did really poorly on exam 1 and you made like a 50 on exam 1, but then you make a 70 on the final exam. Well, that 50 will get replaced with the 70, and so that will be a big help to you at the end of the semester. So kind of keep that in mind as you go through the semester, okay? All right, so today our goal is to pretty much finish up rational expressions. If you think about what we have done so far with rational expressions, so far, we have done simplifying rational expressions And remember, a lot of you use the word reducing when we talk about that, right? Where you're reducing a rational expression or a fraction to lowest terms. We have talked about multiplication. We've talked about division. We've talked about now addition and subtraction, which is probably, for the most part, most people's most difficult part of the chapter is addition and subtraction. And then we've talked about simplifying complex fractions. We've looked at what a complex fraction is, and how to take a complex fraction and actually rewrite it as a simple fraction. So I've done a lot of different things having to do with simplifying rational expressions and dealing with operations with rational expressions. And so now what we're going to do is we're going to turn our attention to equations. And if you think about it, this is exactly what we did with polynomials. With polynomials, we started out at the very beginning of the semester doing a really quick rundown on multiplication of polynomials, adding like terms and subtracting like terms, things like that. And then we did this big unit on factoring polynomials. So we did all these things with polynomials. And then at the end of the chapter, what did we do? We looked at equations that involve polynomials when we talked about quadratic equations and how to solve those. And so now we've done exactly the same thing with rational expressions. We've gone through all this different stuff having to do with simplifying rational expressions, taking rational expressions and making them look different, and learning how to add, subtract, multiply, and divide them. And so now what we're going to do is we're going to finish the chapter by looking at equations that involve rational expressions, and a little tiny bit with word problems, and learn how to actually deal with equations that involve these kinds of expressions. We will do the same thing when we start up the next chapter next week, when we start looking at radicals and exponents. We will do a whole bunch of stuff having to do with simplifying radicals, simplifying square roots and cube roots, a lot of different things having to do with dealing with radical expressions, and some with exponent expressions. And then we will finish the chapter by looking at equations that involve radical expressions. And then once we've done that, then we've kind of finished all this kind of hardcore algebraic simplification stuff that we've done, that we're doing in algebra. And we're going to turn our attention the rest of the semester to functions, graphing, things like that. It's a really different way to finish the course than what we've been doing, and that what we will do for the next probably 3 or 4 weeks still. So the last part of the course is really different than the first part of the course. I would say the last third of the class is really different than the first 2/3 of the class. It's probably the way to look at it. All right, so our goal today is rational equations and solving rational equations. Now, a rational equation, that word now, rational, should bring something to mind immediately to you as an algebra student. It should bring to mind immediately the word fraction, right? That when you see that, you're talking about a fraction. And so we're looking at equations here that have fractions in them, right? And how we want to solve those equations. So I am operating in section 8.6 of your textbook, and we're going to be working problems out of section 8.6 for a while here, and then we'll look at it. Like I said, we'll finish the day with some word problems and finish that up. Now, if you remember, we have the equivalent fractions property. We've talked about that, so there's a little bit that we need to talk about here. The equivalent fractions property, if you remember, we've used that over and over again in this chapter so far. And remember, basically the equivalent fractions property said that if you had a fraction, a over b, who cares what a and b are, right? They could be really complicated expressions, really simple expressions. But the equivalent fractions property basically stated that as long as you multiplied the top of the fraction and the bottom of the fraction, the numerator and the denominator, by the same number, that was legal to do, right? That was always okay to do, and that the fraction you ended up with when you did that, AC over BC, was equivalent to the original fraction, right? So these two fractions right here are equivalent fractions. So that's why, right, we could take 3/5 and we could multiply it by 2 over 2, right? Remember, what are we doing? We're multiplying numerator and denominator by the same thing, right? And you get 6 over 10. And what's true here? 3/5 and 6/10 are equivalent fractions, right? They are the same fraction, just written in a different form. And then as algebra students, we looked at maybe somewhat more complicated expressions, but we used the same property. So like if you had x plus 1 over x minus 2, right, that it was legal, again, to multiply top and bottom by the same thing. And who knows what it might have been. Let's say something maybe like x minus 4 over x minus 4, that was a legal thing to do, right? And that the fraction you ended up with here, that fraction right there, was equivalent to the first fraction. Even though they look really different, right? They're really the same fraction, just written in a different form. So the equivalent fractions property told you it was okay to multiply the top of a fraction and the bottom of the fraction, the numerator and the denominator, by the same thing. And that we use that to our advantage with complex fractions, right? So like we had 1 minus 1 over x over 1 minus 1 over y. What we talked about was that to simplify this, we would use that property and multiply the top and the bottom by the same thing. But in particular, we'd multiply top and bottom by the least common denominator of all those, right? And what are we doing? We're really multiplying top and bottom by the same thing. And so our resulting fraction was equivalent to the first fraction, right? So we would get xy over 1 minus xy over x over xy over 1 minus xy over y. And the reason why we did that with complex fractions is that it allowed us to cancel out the little tiny fractions that occurred in here, right? And what did we end up with? We ended up with, like in this problem, xy minus y over xy minus x. And just like we saw with the problems above, what do we know? That the original fraction and the resulting fraction are equivalent because of the equivalent fractions property, right? That all we did was multiply the top and the bottom by the same thing. So the reason why I'm going back over this is because students confuse what we're about to do with this property right here. All this property is doing is allowing you to rewrite a fraction and rewrite the way it looks, right? You're changing the way an expression looks here. Changing the way an expression looks. Right, and you know, like a cosmetologist, a person who, like in a hair salon or someplace like that, what do? You go to a place like that to change the way you look, right? A little bit, and that's what we're doing. We're being cosmetologists for algebra here. We're changing the way a fraction looks. I'm not saying we're necessarily going to making it look better, but we're making it look different, and we wanted to make them look different because it was helpful. The new form might have been helpful to us instead of the original form. Right, so it's changing the way an expression looks. I'm underlining the word expression because none of this has to do with equations. What do we start with on all of these problems? If you look at the boxes on the left, those are all expressions, right? And there's no equal sign in those boxes, right? These are all expressions here at the beginning, right? When I say expressions, there's no equal signs in any of those right there, right? And that is not what we're talking about in this next section, right? In this next section, we are talking about equations. We're talking about statements that actually have an equal sign in them. And so these are not equivalent fractions property problems that we're going to be talking about. Instead, we're using another property that you use all the time as an algebra student. And when I say that, like, see, look with equations, you have you have what might be termed an equivalent equations property, right? And that equivalent equations property says that if you have an equation, it's okay to do the same thing to both sides of an equation. So like if we had, for example, x plus 6 equals 10, something super, super easy. What do you know? You know that it's legal to take that in an equation like this and take both sides of that equation and subtract the same number from both sides, right? And so now what are you doing? You're not using an equivalent fractions property. You're not multiplying top and bottom by the same thing. What you're doing is you're operating on left and right side of the equation, and you're saying it's legal to do the same thing to both sides of an equal sign, right? And so you get, in this case, you get x equals 4, right? And what do you know? That this resulting equation, even though it's different than the original equation, it's still equivalent. In other words, they still have the same solution set, right? The solution set to this one was 4, and the solution set to this one was 4, right? That the equations were the same, had the same solution. Those are called equivalent equations. And so what about this property, this equivalent equations property? It states that it's legal to do the same thing to both sides of an equation. And that involved also, like with fractions, for example. So like if you had 3x equals 50, right? What did you see? That it was legal here to take that equation and multiply both sides by 1/3, the reciprocal of 3, right? Which is, by the way, the same thing as dividing by 3. So if you wrote it that way, that would be absolutely okay. And then what would you end up with here? You'd end up with x equals 50/3. And what do you know? That this equation and this equation, since you use this equivalent equations property here, right, what did it state? That those two equations had to be equivalent equations. All right, so we're using that property, and notice that's distinctly different than this previous page, right? This previous page, what did we start with? We just started with an expression. And what did we do? We did the same thing to the top and the bottom, to the numerator and the denominator. We used this equivalent fractions property. We ended up with an expression at the end, right? The expression at the end was equivalent to the original expression. It means they had the same value if you use numbers in there for the variables. So we're doing in this case, we're doing something different, right? We're operating on both sides of an equal sign. We start with an equal sign, so we have an equation, and we're operating on both sides of that equal sign. And what are we going to try to do? We're going to try to get rid of the fraction. So like in your textbook on section 8.6, this is on page, by the way, page 963, problem number 304, you have this equation. You have 5/6 plus 3. Now in the book, they have 3 over b. My b's look so much like my 6's. I'm going to not do that. I'm going to put 3 over x. Doesn't matter. It's a dummy letter, so it doesn't matter what letter we use there. Right, so what do we want to do here is we want to get rid of the fractions, and we want to use the property above to get rid of the fractions. When I say the property above, what does the property above tell us that we're allowed to do? It tells us that we're allowed, see, this is an equation now, right? This problem that we're working on here has an equal sign in it, right? This is an equation right here. It's not just an expression that we're trying to change the way it looks. It's an equation that we're trying to make into a different looking equation. In particular, what's our goal here is to get rid of the fractions. And so we are allowed here to multiply both sides of this equation by the same thing. This is not a top and bottom problem. This is a left and right problem, right? And so that's another way to look at this, by the way, is that equations are left and right problems. In other words, it's legal to do something to the left and right side of the equal sign, but expressions are top and bottom problems. That here it's legal to do the same thing to the top and the bottom of the fraction, right? So here, this is a left and right problem. This is an equation that we're trying to make look different. And the deal here is we want to get rid of the fractions, right? That's what we're talking about. And so we're going to use a trick that we started talking about with complex fractions. We multiply the left and the right side of this equation by the LCD, which is 6x over 1. In this case, it's 6x over, and we multiply top or left and right by the LCD over 1. So let me erase that and put it in a different color here. So this would be 6x over 1 here and 6x over 1 here. Notice it's not 6x over 6x. That's what I'm trying to get across to you with these last two pages. That you're not doing the same thing to the top and the bottom. You're doing the same thing to the left and the right. So you don't care if the top and the bottom are the same number. We're going to leave the bottom as a 1. We don't want to put anything else in the denominator. We want to get rid of all the denominators, right? So that the way we do that is we multiply left and right side by the LCD over 1. And so that's, in general, excuse me, one way you could look at that is that this process of getting rid of the fractions means that when you have an equal sign, right, like this, that you're going to multiply left and right side by the LCD over 1. That's going to be your strategy for doing this kind of problem. Let me make the arrow look a little bit better there as far as pointing right to the problem there. There we go. And so getting rid of the fractions is going to be a left and right thing. We're going to multiply left and right side by the LCD over 1. So that's going to be our strategy. So now look what happens when we do that. You get, in this problem, you're using the distributive property here, right, on that side of the equation because there's addition there. So you get 30x over 6 plus 18x over x equals 6x over 3. You see how I multiplied everything by 6x over 1. And now look what happens. The 30 and the 6 divide out, and you get 5x. And on the next fraction, the x's divide out, and you're left with 18. And on the other side of the equation, the 6 and the 3 divide out, leave me with a 2, and I get 2x. And what happens? You started with an equation that had fractions. You multiplied the left and the right side by the LCD over 1, and when you did that, you're left with an equivalent equation, right? You're always left with an equivalent equation when you do this. That means the solution to that last equation is the same as the solution to the first one, but it doesn't have any fractions, right? All fractions are gone. That is your goal. Get rid of those fractions. You're not multiplying and I'm going to really try to say this a lot, so you're going to get sick of me saying this, but with equations, you're not multiplying the top and the bottom by the same thing. You're multiplying the left side and the right side by the same thing, and it's going to always be the LCD over 1. Always, always, always the LCD over 1 to get rid of the fractions. And you can tell the reason why, probably you've surmised this, the reason why I'm making such a big deal about this is because students are always, always, always getting these processes confused. And they take an equation like this and they end up multiplying the top and the bottom by the same thing. And then they're going to mess the problem up by doing that, right? And so you need to make sure you're really clear on what kind of a problem you're dealing with here. Now you've got this equation, with no fractions in it. And so to finish this, what are you going to do? You're just going to solve this equation, and the equation might be linear, it might be quadratic. In this case, this is a linear equation, right? All the x's are raised to the first power. And so you're just solving for x here. And so what I could do here, probably the easiest thing to do, I'm going to write the equation down again. 5x plus 18 equals 2x. Is I'm going to go ahead and subtract 2x from both, I'm sorry, subtract 5x from both sides. And so that leaves me with 18 equals negative 3x. And then finally, to finish the problem, I'm going to divide both sides by negative 3. And that would give me that negative 6 is equal to x. And I've solved the original equation. I've got negative 6 equals x. And that is the solution to that original equation. Right, and remember, you can always check your solution to these problems, right? You can take your solution and substitute it into the original equation and make sure it gives you a true statement. Not a bad idea to do that. So let's go to the next screen and let's write down the equation again. So this is the check from the last problem. Right, what our original equation was 5/6 plus 3 over x equals 1/3. We found the solution to be negative 6 equals x, right? So when you substitute negative 6 in here, right, so check, x equals negative 6. You get 5/6 plus 3 over negative 6 equals 1/3. And so, go ahead and leave negative 3 over negative 6. Just leave that in terms of 6 because you've got common denominators there. And so this is really just 5/6 minus 3/6 equals 1/3. And notice 5/6 minus 3/6 is 2/6 equals 1/3. And sure enough, you get 1/3 equals 1/3, right? And so it does check. All right, so you've got the solution to the equation. So negative 6 is the solution. All right, so this is our process. This is what we're going to do then on these problems to try to solve these. And so now we are going to work some more examples, and there are some things that we need to talk about, and the problems are going to get, unfortunately, more complex as we go through this. So we'll start off with some relatively straightforward problems, but we will be finishing with some relatively messy problems when we're done. All right, so we have 3a plus 2 over y equals 1/4 is our next equation. Very similar to the last problem. What do we want to do? It's an equation, right? We want to multiply left and right by the LCD over 1. So the first, so we want to get rid of the fractions. We know that we have stuff on one side and stuff on the other side. And what are we going to do? We're going to multiply both sides by the LCD over 1 to clear the fractions. Right? Notice that's not the LCD over the LCD. It's not the same thing in the top and the bottom. It's always going to be a 1 in the bottom when you do this kind of problem. So the least common denominator here is between 8y and 4. The smallest number that 8 and 4 divide into is 8, right? 8 divides into 8, and 4 divides into 8. So the LCD has to have an 8 in it, and then it also must have a y. And so we're taking our equation, and we're going to put brackets around both sides of the equation, like that. And we are going to multiply both sides of the equation by 8y over 1, like that. Right, and then when we do that, on the left side, this is the distributive property. And if you see how things cancel out, you don't have to write this next step out, but I'm going to write this step out for a while here. I'm actually going to multiply it and not do any reducing. Some students will do reducing in the same step here. I'm not going to do that at least yet. So you get 24y over 8. And then 16y over y equals 8y over 4. And so then you go through, once you've multiplied, and everything should cancel out. All the denominators should go away in this next step, right? So the 24 and the 8 divide out and leave you with the 3y. In the next fraction, the y's divide out and leaves you with the 16. And on the right side of the equation, the 8 and the 4 divide out and leaves you with the 2y. And so what happened here, you started with an equation that had fractions. You multiplied both sides by the same thing, the LCD over 1. And you ended up with a fraction, or I'm sorry, an equation that has no fractions, right? No fractions left in this equation. Yay, right? That's what you're trying to do. You're trying to change the way the equation looks. All right, and then you solve this equation. You think about what kind of an equation this is. In this case, this is linear. All the y's are raised to the first power. And so you could solve this for y, a couple ways, but I'm going to subtract 3y from both sides. And so that gives me 16 equals negative y. And then because it's negative y there, I'd have to divide both sides by negative 1. And I get negative 16 is equal to y. And so this, and you could check it just like we checked the last problem. You'll find that this is a solution and that negative 16 is the solution to this equation. All right, so hopefully you found these first couple of problems. You're going, yeah, I think I kind of understand what's going on here. Hopefully that's the case. And, if for those of you who are listening to me live, please shout out if you have a question about something as we go through this. All right, the next problem I want to look at is number 314. And so we're going to slowly now start getting a little bit more complicated. This one is 1 minus 7 over q. My q's don't look all that great. Equals negative 6 over q squared. Like that. All right, so this is a problem. It's a rational equation, right? It's got these fractions in it. We're going to try to get rid of those fractions. We need to identify the least common denominator. And if you look at all the denominators, the only factor you see in any of the denominators is a q. So I need a q in the LCD. And then the largest power that the q is raised to is the second power. And so I've got to put it in the LCD as q squared. And so this is a problem where I'm going to multiply both sides by q squared over 1. So here's my equation. I'm going to multiply both sides by q squared over 1, LCD over 1. On the inside, that 1 in the first fraction, you could write it as 1 over 1 if you wanted to make it look like all the other fractions. Not a bad thing to do. You don't have to do that by any means. If you know that that's what it is, you don't have to deal with it that way. But it does make it look like the other fractions at least. So over on the left side, you're using the distributive property. And multiplying on the right side also. So you get q squared minus, and technically q squared over 1 minus 7q squared over q equals negative 6q squared over q squared. Now, like I said, you may or may not have to write that particular step out. I like to write it out, especially as I'm getting used to doing these kinds of problems. So what happens here, in the first fraction, well, that's just a 1 in the denominator, so I just have a q squared there, so no big deal there. The second fraction, one of those q's does divide out, and I'm left with a q in the numerator there, and so this is just 7q, technically 7q over 1. Equals, and then on the right side of the equation, the q squareds divide out, and I'm left with negative 6. So once again, what happened? We started with an equation that had fractions in it. We multiplied left and right side by the LCD over 1, and we are left with an equation that has no fractions. All right, that's what we're trying to do. That's an equivalent fraction, an equivalent equation, remember, so that means its solutions are the same as the solutions to the original equation. Now this equation is quadratic. Right, it's got a q squared in it. And so remember with quadratics, when you see that, you've got to set the equation equal to 0, right? So this is different than the last couple of problems for that reason. So I could add 6 to both sides. And you get q squared minus 7q. Please don't add the 7q and the 6 together. Those are not like terms, right? Don't add things together that are not like terms. So you're just adding 6 to both sides, and you end up with that equation. And remember here, the idea is to factor this equation, factor this expression, right? And use the zero factor theorem to solve this. So you have q minus 6 times q minus 1 equals 0. Set each factor equal to 0, and you end up with q equals 6 and q equals 1. And so this particular problem ends up, this particular equation ends up with 2 solutions. These will both check. And so you end up with 6 and 1 as solutions. Now, I've been kind of talking a little bit about the check at the end. What we're going to find as we start going through the next couple of problems, believe it or not, is sometimes you end up with solutions that do not check at the end of the problem. And so that is something that we need to talk about as to what's going on with that, And so you'll gradually start seeing problems like that over the next couple of problems. I'll show you what I'm talking about. So let's look at the next problem I want to do is just an example. Let's say we have 3 over x plus 6 equals 5 over x minus 4. Now, this particular rational equation is a little bit, this is actually in a better form than the first few problems we did. This is an example of a rational equation that is also what we call a proportion. It's a proportion because it's just one fraction on one side of the equation equals a fraction on the other side of the equation. See, notice if you look back, this problem was not a proportion because the left side of the equation was not a single fraction. Right? When we looked at these two problems, these were not proportions because there was not a single fraction on both sides of the equation. On both of these problems, you had 2 fractions on the left side. Right? So none of these problems have been proportions. This problem in particular is a proportion. It's a single fraction equals a single fraction. And it's easier to get rid of the fractions when you have a proportion. So it's easier to eliminate fractions. And the reason why is because when you have a proportion, A over B equals C over D, it is always true that the cross products of the two fractions must be equal. And when I say cross products, I'm talking about multiplying across like that. Right? Those are the cross products. And so notice this is the cross product BC right here, and this one is the cross product AD right here. And it's got to be true that if the original fraction, original fractions are equal to each other, then the cross products must be equal also. So you can take advantage of that when you have a proportion, and you can just use this process of cross multiplying. Because you know that the cross products must equal each other. So when you notice you have a proportion, it's an easier problem to solve if you remember that idea that it's a proportion. And so notice in this case, the cross products are 5 times x plus 6, and 3 times x minus 4, right? And those have to be equal to each other. And so now you end up with an equation that has no fractions in it once you cross multiply, right? And then you just solve the resulting equation. And so you get 3x minus 12 equals 5x plus 30. It's a linear equation. All the x's are raised to the first power. So you subtract 5x from both sides. You get negative 2x minus 12 equals 30. And then you add 12 to both sides, and you get negative 2x is equal to 42. And then finally, you divide both sides by negative 2. So you have negative 2x divided by negative 2, and 42 divided by negative 2. Then you get x is equal to negative 21. Now, and that's the solution to this equation. Negative 21 is the solution. Now, what can happen here sometimes is that when you have an equation like this, so like you have 3 over x plus 6, plus or minus something, blah, 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 let's say. Notice that if you tried to check x equals negative 6 in this equation, you get 3 over negative 6 plus 6, and that's 3 over 0, which is a meaningless expression, right? That's a meaningless expression. And so that can happen when you have a rational equation, is you can solve it, do everything right, multiply both sides by the LCD over 1, but end up with a solution at the end that gives you a 0 in the denominator in the original problem. So like in our particular problem, 3 over x plus 6 equals 5 over x minus 4, there are some x values that we knew we would not be able to, we could not get in this problem. These are what we call restricted values, right? And all you do is look at the denominators, and the x plus 6 tells you that x can't be negative 6, because if you tried to use negative 6 there, you'd get a 0 in the denominator. And x minus 4, that factor tells you that x can't be 4, right? Because that would give you a 0 in the denominator. And so those are what we call restricted values for this equation. When I say restricted values or just restrictions, what I'm saying is that we could have identified at the beginning of the problem that we are not allowed to get negative 6 or 4 as solutions to this equation. And if we do, then we have to throw them out of the solution set. You will be asked to find restricted values sometimes on problems. On your exam 2, I will give you an equation, and one thing I'll ask you right away is to state the restrictions on the equation. Right? I want you to actually write those down. All right, so keep that in mind as we go through these problems, and you'll see that sometimes the restriction does come into play in the problem. Okay, so this is problem number 320, so we're going to get a little bit more complicated now. You have 5 over y minus 9 plus 1 over y plus 9 equals 18 over y squared minus 81. Now remember one thing, so what do we have to do here at the beginning? We have to multiply left and right side by the LCD over 1, but I can't find the LCD until I have all the denominators factored. And so if there's any denominators that need to be factored, you do that at the beginning of the problem. And so in this case, the y squared minus 81 factors as y plus 9 times y minus 9. Right, it's the difference of two squares. And so now I've got all the denominators factored. And so my LCD, my least common denominator, I write down all the factors that I see in any of the denominators. And so there's two of them, y minus 9 and y plus 9. And I look to see if any of them are raised to a power, but none of them are. And so I'm good right now. That's my LCD, y minus 9 times y plus 9. And so what I'm going to do here is I'm going to multiply both sides of this equation. And so I put brackets around both sides, but I'm going to multiply both sides by that LCD over 1. Remember, that's what you're doing. Multiply left and right side by the LCD over 1. So this is y minus 9 times y plus 9 over 1 on this side, and y minus 9 times y plus 9 over 1 on this side. Right? Left and right side have to be multiplied by the same thing. All right, and hopefully you're starting to get at the idea of, as you multiply this out on the left side right here, how things are going to cancel out. So this will probably be the last step, the last problem where I write this step out. But when I multiply using the distributive property, I have 5 times y minus 9 times y plus 9 over y minus 9. That's my first fraction. And you can see why this starts to get to be a hassle to write this step out. And you have y minus 9 times y plus 9 over y plus 9 equals, and then 18 times y minus 9 times y plus 9 over 1. I'm sorry, whoa, definitely not over 1, over y plus 9 times y minus 9. There we go. All right, so I've multiplied everything by the LCD over 1, and now I go through and I cancel things out, right? And so the y minus 9s divide out, the y plus 9s divide out, and then over here in the last fraction, both factors divide out. And so you're left with 5 times y plus 9 plus y minus 9 equals 18. And boom, you've got an equation with no fractions. Yeah, that was what we're trying to do. This is also a linear equation. All the y's are raised to the first power, so I'm just solving for y, getting y by itself on one side of the equation. And so you have 5y plus 45 multiplied there, plus y minus 9 equals 18. And I just remember there was one thing I forgot to write down here at the beginning, is notice that, and I should have done this at the beginning of the problem, and I just kind of overlooked it, is I should have written down the restrictions from the original equation. Once we've got everything factored, we can tell what the restrictions are. We can tell what y values we're not allowed to get, right? From y minus 9, we're not allowed to get y equals 9, right? Because 9 minus 9 would be 0. Whatever y value makes that 0, you don't want. And from y plus 9, right, we get the restriction that y can't be negative 9. All you're doing is setting the factor equal to 0 and solving. Right, so if you want to, you could actually formally set it equal to 0, like I'm doing off to the side here, and solving those for 0. And so that's how you find the restrictions. Just take those factors from the denominator. You don't care about the numerators, but the denominators, you just set them equal to 0. And so I know that I'm not allowed to get 9 as a solution here in this problem, and in case that comes up, or negative 9. All right, so let's solve this. So you have 5y plus y is 6y, collecting like terms, and 45 minus 9 would be 36, equals 18. And then go ahead and subtract 36 from both sides. And I get 6y equals negative 18, and then divide both sides by 6. Then I get y equals negative 3. The negative 3 is not one of the restrictions, and so that's the solution to this equation. Negative 3 is okay, is the solution. All right, we've solved this equation. Like I said, sometimes you're going to come up with one of the restrictions when you solve a problem like this. You have to be prepared for that. All right, so let's move on to problem number 328. We have a couple of problems to look at here, and then a word problem to finish off the day. So this is problem 328. You have w plus 8. This will take me a while to write. Over w squared minus 11w plus 28 equals 5 over w minus 7 plus 2 over w minus 4. All right, so this is a pretty big step up from the first couple of rational equations we looked at. So remember, the first thing we do is we factor all the denominators, make sure everything's factored. And so the first denominator does factor w minus 7 and w minus 4. And then what we are going to do is, at that point, we're going to write down the restrictions. So remember to do this at the beginning on this problem. So the restrictions are from w minus 7, right, is the w cannot be equal to 7. right? And from w minus 4, we get that w cannot be equal to 4. Those are our restricted values for this equation. It means we would not be allowed to write those as solutions here, because those cannot be solutions to this equation, because they give you meaningless expressions if you try to check them. All right, and so now what we are ready to do is we're ready to multiply both sides of this equation by the LCD over 1. So I put brackets around the left side and the right side, and I multiply both sides by w minus 4 times w minus 7. That's our LCD. Those are the only factors I see in the denominators. So I'm going to multiply both sides by w minus 4 times w minus 7. That's my LCD. Remember, that's the LCD over 1. LCD over 1, and this is the LCD over 1 on this one also. All right, so on the left side of the equation, what happens? Well, the w minus 4 and the w minus 7 would both cancel out, and we'd be just left with w plus 8 equals. All right, now I'm going to try to go ahead and divide things out in this step right here. So this is the distributive property. Remember, you're taking this LCD over 1 and multiplying by both of those fractions. So when you multiply by the first one, notice that you'll have a w minus 7 divide out in the top and the bottom. And so that would leave me with a 5 and a w minus 4. Right, the w minus 7 would divide out there. And on the second fraction, the w minus 4 would divide out. And I'd be left with a 2 plus 2 and then a w minus 7. Right, so I went ahead and divided everything out as I was multiplying here. All right, so then I solve this equation. I multiply everything out, and when I multiply everything out, I see that I have a linear equation. Right, all the w's are raised to the first power here, so this is linear. So I'm going to collect like terms and then solve the equation for w. Just get the w by itself. So you have 7w minus 34 on the right side of the equation when you collect like terms there. And then I will subtract 7w from both sides. So that gives me negative 6w plus 8 equals negative 34. And then I'm going to, remember, you're solving for w, so you're trying to get that w by itself. So I'll subtract 8 from both sides, and I get negative 6w equals negative 42. And then I'll finish this by dividing both sides by negative 6. And look what you get. You get w equals 7. But notice that w equals 7 was a restriction, right? W equals 7 is a restricted value. And so what do you have to do? You have to throw x equals 7 or w equals 7 out of the solution set. Well, if 7 is the only solution, and it can't be a solution because we have to throw it out, that means there's no solution to this equation, right? Because w equals 7 has got to be thrown out. And so depending on, like in WebAssign, you might see braces with nothing between them. You might see no solution written out in words. On a test, I'd be thrilled with either one of those. It would not make any difference how you wrote it. I'd be super happy either way. Okay, so that one was different. We ended up with a restriction on that particular equation. All right, next problem I want to look at. Hopefully you are following this okay, and everybody's okay with the problems we've looked at so far. And so I'm going to look at number 338. So you've got p over p plus 7 equals 98 over p squared minus 49 plus, and then that's just plus 8. And that 8 at the end would be technically 8 over 1. So don't forget that you're going to write down the restrictions, but the first thing you do on a problem like this is factor all of the denominators that you see in the fractions. So in the first fraction, the p plus 7, there's nothing I can do there. But the p squared minus 49 is the difference of two squares. And so that factors p plus 7 times p minus 7. And then the 8, I'm going to write it so it looks like the other fractions is just 8 over 1. All right, and so now we're ready to write down the restrictions. The restrictions in this case, we look at just the denominators, and you get that p cannot be negative 7 from the p plus 7, and from the p minus 7, you get that p can't be 7. So 7 and negative 7 are restrictions here. Right? You can't get those as solutions to this equation. Okay, so we multiply left and right side by the LCD over 1. And in our problem here, the LCD is going to be p plus 7 times p minus 7. Those are the only factors we see in the denominators there. All right, so that's what we do. We're going to multiply left and right side by p plus 7 times p minus 7 over 1. And we're getting rid of these fractions. So on the left side of the equation, the p plus 7 divides out, and you're left with a p times p minus 7. And on the right side, you're using the distributive property over here. When you multiply by the first fraction, both the p plus 7s and the p minus 7s will both divide out, and you'll be left with 98. Plus, and then in the second fraction, the 8 over 1, nothing divides out there, and you're just left with 8 times p plus 7 times p minus 7. Right? Because there's no factors in the denominators at all there. All right, so now we're going to multiply stuff out, and there's some work to do here on this problem. You got p squared minus 7p on the left side equals 98 plus, okay, now how do you take 8 times p plus 7 times p minus 7? That's three numbers being multiplied together. That is absolutely not distributing the 8 through on both of those factors because it's all multiplication. So remember how you multiply three numbers together is you just take two of them and multiply together, and then you take that answer and multiply it by the third. It does not matter what order you take these in. So what makes sense to me to do is to take the p plus 7 and the p minus 7 and multiply those together first. Because I know that that's the difference of squares, and that just gives me p squared minus 49. And then I'll take that answer and I'll multiply through by 8. So you have p squared minus 7p equals 98 plus 8p squared minus, okay, so this is going to be big, 8 times 49. Let's see, so 8 times 40 is 320, and 8 times 9 is 72, so you end up with 392. Yuck. This equation is quadratic because I have p squares in here. And so I need to set this thing equal to 0. I need 0 on one side of the equation. Now let's see, let's just clean this up a little bit. You have p squared minus 7p, and on the right side you have 8p squared, and then 98 minus 392. What do you get? Negative 294 there. And you definitely want to check my arithmetic there, but I believe that's right. That you end up with minus 294. All right, and then you want to get set equal to 0. Since the 8p squared is on the right side, and that's the bigger p squared term, I'm going to move everything over there. So I'm going to subtract p squared from both sides. I'll take 2 steps to do this. So you get negative 7p equals 7p squared minus 294. And then I'm going to go ahead and add 7p to both sides, and I get 0 equals 7p squared plus 7p minus 294. Yuck, the numbers are huge here. Now, what I'm hoping is that 7 is a common factor, and 7 does, sure enough, divide into 294. So thank goodness that kind of saves me here. I factor out of 7. Let's see, 7 goes into 29. Let's see, 4 times. That's a minus 4. So it's 42. Yeah. Much easier to factor that one. So you end up with p plus 7 times p minus 6. And that 7 just trails along as a factor in the front. But remember, when you have a constant factor there, you do not get a solution. You can ignore that 7 at the beginning. And so you end up with p equals negative 7 and p is equal to 6. And then notice that p equals negative 7 is a restriction at the end of the problem here. And so what do? You throw that out. And so the solution set to this equation is just 6. 6 is not a restriction, and so that one's okay to use as a solution to this equation. Notice these are pretty lengthy problems. There's no question about it. So it takes a while to get through these. All right, and so let's finish this with a word problem or two. All right, so let's, these word problems that I'm going to look at are word problems, applications, if you'd rather call it an application. I'm going to look at what are called work problems. And so we want to look at a couple of work problems to finish the day off with here. So, so an example of a work problem is, let's say that Tom can mow a yard in 3 hours, right? And let's say that Ed can mow a yard in 2 hours. Right, so let's say that we've got those two pieces of information. Then the question would go like this: how long would it take to mow the yard if Tom and Ed work together? But that would be our question here. Now, if Tom and Ed get along, then what should happen? They should help each other out. And if they don't get along, let's say they're brothers, then maybe it takes them longer to do this because they fight in the middle of mowing the yard. But we're going to assume that Tom and Ed get along really well, and so they both help each other out. Now, Ed is faster than Tom here, right? Because it only takes Ed 2 hours to mow the yard. It takes Tom 3 hours. But if they work together, we expect that they're going to help each other out. And so Tom is helping Ed here. And so our answer better be less than 2 hours, right? If Ed is mowing by himself, it takes him 2 hours. If he has Tom's help, even if Tom's a little bit slower, Tom should help him out. And so the answer should be less than 2 hours, right? So the answer should be less than 2 hours. This is a classic example of what we call a work problem. All right, where you got a couple things working, and then what happens if you combine how they're working. All right, so what I usually do is I make a little chart for this kind of problem. And so I'll write and the rows will be the people that are working here, the things that are working. So in this case, it's Tom, it's Ed, and then remember, there is a third case here, and that's Tom and Ed. Right? It's Tom by himself, Ed by himself, and it's Tom and Ed working together. So the time that it takes Tom to mow the yard is 3 hours. And the time it takes Ed to mow the yard is 2 hours. Now the question is, how long does it take them to mow the yard together? That's our question here. We don't know the answer to that, and so that's a variable here. So we'll just call that x. If you want to call that t, that's fine for time. But we don't know what that is. That's what we're actually trying to find. Now this next part is the critical part. The last column here is how much of the yard do they mow in 1 hour? And so how much of the yard do they mow in 1 hour? Right, that's the last column right there. So I want you to think about it this way, that, for example, Ed takes 2 hours to mow the yard. So if Ed works at a steady pace, if you think about it for a second, well, in each hour then, Ed ought to mow half the yard, right? And so you write a half right here. Right? He mows half the yard in the first hour and half the yard in the second hour. So in 1 hour, he mows half the yard. Tom, same thing, but he takes him 3 hours. So if he's working at a steady pace, what would be true here? Every hour, he would mow a third of the yard. A third the first hour, a third the second hour, a third the third hour. So that would be, we put a third there for Tom. Notice that those are always reciprocals, right? That's a reciprocal right there. And that's a reciprocal right there. And so that's always going to be true. With the first column being time and then the second column being how much in 1 hour or 1 minute or 1 day, whatever the time units are, that are always going to be reciprocals. And so this last one would be a reciprocal too. So how much do they mow in 1 hour if they're working together, Tom and Ed together? That would be 1 over x. It'd be the reciprocal of that first fraction, of that first number there. And now finally to write an equation. Well, what would have to be true here is that if Tom mows a third of the yard in that first hour, and Ed mows half of the yard in that first hour, then that would be how much they do together in 1 hour. And that's our equation right there. Just add the first two fractions together and it should be equal to the third fraction. So you get 1/3 plus 1/2 equals 1 over x. It's actually a pretty simple process. And what happens here? We end up with a rational equation, the kind of equation that we've just been talking about. So in this case, really a much simpler rational equation than what we've been talking about also. So that's nice. So all you got to do is find the least common denominator and clear these fractions. The least common denominator here is 6x. And so what I'm going to do is I'm going to multiply left and right side of this equation by 6x over 1. All right, so I put brackets around both sides, and I'm going to multiply both sides by 6x over 1. Remember, that's what you do. You multiply both sides by the LCD over 1. And let's see what happens. We should end up with an equation that has no fractions. So you get 6x over 3 plus 6x over 2 equals 6x over x. And notice all the fractions, sure enough, disappear here. You end up with 2x plus 3x equals 6. Or 5x equals 6. Right? It's a linear equation. You just divide both sides by 5 and you get x is 6/5. And what did x represent? X represented the time that it took Tom and Ed together to mow the yard. And so sure enough, that would be 1 1/5 hours. A fifth of an hour, by the way, is 12 minutes. And so that answer does make sense, doesn't it? Because we talked about that the final answer to this problem should be less than 2 hours, and we got that as 1 hour and 12 minutes, all right, 1 1/5 hours, so 1.2 hours if you want to write it that way. And so that actually makes sense in the context of this problem, and so we've actually solved the problem. All right, so I was looking for one more problem like that, and then in the book, and then we're going to that will finish up our work problems. And so I was looking for one more problem like that. And I'm not, okay, so this is on page 990 of your book. And we've got, I'm going to look at problem 452. So this is page 990. This will be our last problem of the day. Page 990, problem number 452. And it said Paul can clean a classroom floor in 3 hours. So this is Paul. And for his time, we would write 3 hours. When his assistant helps him, so this is Paul and his assistant together, notice. So Paul and assistant. Then it takes him 2 hours. Right, so we're going to put 2 there. And so the question is, when his assistant, how long would it take his assistant to do the job alone? And so the assistant goes in here, and that would be our unknown. That would be X in this problem. So notice when it's slightly different in that you're given different information to start off the problem. So the next column is how much in 1 hour. And remember, you're talking about cleaning a room here. And so for Paul, that would be 1/3 of the room in 1 hour. The assistant would be 1/x, and Paul and the assistant together would be 1/2. And remember, those are always reciprocals of the time column there. And so what happens here? We get that if we add how much of the job Paul does in an hour, plus how much his assistant does in 1 hour, that would be equal to how much Paul and the assistant do together in 1 hour. And so this would be 1/2 right here. All right, and so very, very similar kind of equation. It's just that the variable is on the opposite side of the equation. The least common denominator here would be 6x. And so we're going to multiply left and right side of the equation by 6x over 1, right, to clear out the fractions. So you get 6x over 3 plus 6x over x equals 6x over 2. And so now you go through and you divide out the fractions here, and you get 2x plus 6 equals 3x. And notice in this problem, I can solve for x by just subtracting 2x from both sides. And right away, I get that 6 is equal to x. And so it takes the assistant 6 hours working by himself, his or herself. It takes assistant 6 hours working by themselves. And we've solved the work problem. So you'll probably see a work problem on the next exam, but something pretty straightforward like the problem that I just showed you right here. So, all right. Does anybody who's listening today live, do any of you guys have any questions for me?
No, not at the moment.
Anybody still? Okay, so there's a few of you who are still alive, so that's good. So, or I should say, a few of you who are still awake.